So this video, let's talk about theorem, which is important in the calculus, okay, and also advanced calculus. If a series an converges absolutely, then it converges in the ordinary sense. The converse is not true. So basically, the theorem tells you that if sum of an come, then the sum of an come. So if sum of the absolute an converges, then sum of an converges. Okay, then the converse is not true. Okay, so let's give a proof. Okay, so the proof idea is that we can maybe let xn to be, let's say, k from 1 to n, and we hope to show Sn is cosy. So n from 1 to infinity is cosy. So from the real number results, right, we know that the limit n goes to infinity, Sn exists. Since that Sn is cosy, right? So by the complete, then Sn exists. Okay, so in order to show this is cosy, that means for epsilon greater than 0, we should find n, right? Well, we should find a large integer n such that for n greater than m greater than n, the Sn minus Sm is less than epsilon. Okay, so but we see what is this Sn minus Sm, right? So Sn minus Sm is basically k from m plus 1 to n. Okay, and this guy is bounded by this guy. Okay, but we know what? We know that this an, right, this goes to infinity, converge. Okay, so that means this guy, so that means since this guy converge, right? So this guy is also cosy. This guy is also cosy sequence. So let's maybe we can add Tn to be a k from 1 to n. Okay. So we know that the Tn n from 1 to infinity is cosy. Since we know this converge. Okay, so for epsilon greater than 0, is this n such that we want to show this, right? But we know that there already exists some such that n greater than m greater than n, this Tn minus Tn is already less than epsilon, because this guy is cosy, right? But this guy is just this, so this guy will greater or equal to this guy. Okay, so this proves that Sn is cosy. Okay, so that means Sn converge. Okay, so the key proof is that using property of Tn is cosy to bound this Sn to prove Sn is cosy. Okay, so let's talk about the final remark. So remark is that the converse is not true. Converse is not true. So let me there exists an such that the sum of an converge, but the sum of an absolute diverge. So this is a easy result. You can take an like minus n 1 to n minus 1 divided by n. So your sum of an will be this one. Okay, and this is called a test scoping series. So by the alternating test, this is converge. And actually, you can prove this is just natural log 2. But the famous result is this, right? So, and this is a famous harmonic series, or basically it's just O log. We are bounded by O log n. Okay, and it should be it's theta log of n. So basically, if n increase, then this guy grows bounded by log n. Okay, so this is diverge. Okay, so that's all.